Quick question. What did you have for breakfast 3 days ago? Probably complete radio silence from your brain. But if I ask you to describe your most embarrassing moment from middle school, your brain drops a 4K 60 frame per second remastered movie right in front of our eyes. Why is our brain so widely selective? Why does it hoard random memories from 10 years ago but toss out today's grocery list as soon as you step foot in the store? The answer comes down to one of the coolest features of the human body, neuroplasticity. Today, we're unpacking how your brain literally rewires itself to build long term memories, why your grandma remembers her first date in 1965 better than where she put her glasses 5 minutes ago, and how you can hack this process to remember as much as possible. To understand how memory works, we have to look into our brain's primary workforce, neurons. We have about 86 billion neurons in our body, which make up our brain, spinal cord, and nerves, allowing us to think, feel, and move. These neurons communicate with each other by shooting small electrical and chemical signals to each other across tiny gaps called synapses, which are present between cells throughout your body's nervous system. The ability of your brain to physically change its structure based on experience is called neuroplasticity. Neuro meaning brain, and plasticity meaning moldable. Think of your brain like a lush, dense forest. Every time you think a thought, experience a feeling, or practice a skill, you walk through that forest. Walk through a path once, and you barely trample the grass. But walk through that same path 100 times, and you wear down a clear dirt trail. Walk on it 1,000 times, and you've built a paved highway. Under the same idea as that forest metaphor, neuroscientists have a golden rule that states that neurons that fire together wire together. This just means that when two neurons repeatedly communicate, they physically upgrade their connection through a process called long-term potentiation, or LTP. To describe this, let's hop back into the synapses real quick. When neurons communicate across a synapse, the most common excitatory messenger is glutamate. When the sender neuron fires, it releases glutamate, which floats across the synapse and binds to the receiver cell, releasing positively charged ions into the receiver cell. The receiver cell has multiple channels able to receive communication. However, only one channel, called the AMPA channel, is open to allow these positively charged ions through. There's another channel called the NMDA channel, which remains closed due to a magnesium ion blocking it. But when the sender cell is firing a ton of glutamate, the receiver cell gets so full of positively charged ions that it pushes out that magnesium blocker from the NMDA channel. Once this magnesium ion is removed, enzymes are activated, which insert more AMPA channels directly into the receiver cell's membrane. Although this magnesium ion will come back and plug the NMDA channel again, AMPA receptors always stay open, so more positively charged ions are able to enter than ever before. So now, this receiver cell has more AMPA channels than before, so the same amount of glutamate will now yield a much stronger response. This process also works in the opposite way, in a process called long-term depression, or LTD. This is exactly what you probably think it is. It just means that when a pathway becomes rarely used, proteins are activated that will remove AMPA receptors and weaken those connections, so that these AMPA channels can be used in more active pathways instead. And this is what keeps your brain efficient. So let's solidify that connection between your neurons by reviewing that information and using that path again, because LTP is a foundation of memory. Basically, neuron A sends a message to neuron B over and over. Neuron B says, okay, this seems important, and builds more receptors, like putting on extra baseball gloves to catch neuron A's signal faster, and with less effort next time. Their connection gets stronger so that next time neuron A barely whispers, neuron B instantly gets the message. This physical strengthening at the synapse is the biological basis of learning and short-term memory formation. So, how do those strengthened connections turn into actual lasting memories? Let's enter the hippocampus, an area of our brain tucked deep inside the temporal lobe, shaped a bit like a seahorse. This structure acts like our brain's chief memory director or project manager. When you experience something, say going to a live concert, different parts of your outer brain, the cortex, process different pieces. Your visual cortex processes the lasers and the stage lights, your auditory cortex processes the loud bass, and your amygdala processes your excitement. Your hippocampus steps in, gathers all those scattered sensory pieces, and binds them together into a single memory package, keeping all packages accessible. But the hippocampus doesn't store these memory packages together. It acts more like a temporary processing center, like the RAM in a computer. Through a process called systems consolidation, which mostly happens while you sleep, the hippocampus repeatedly replays the memory network to the cortex. Every night, it nudges those neurons to say, hey, practice this connection again. Over weeks, months, or years, the direct connections between these neurons become so strong and self sufficient that they no longer need the hippocampus to step in as a mediator. So now, when only a fraction of the original experience is presented, such as a familiar scent, that partial input activates all connected and strengthened synapses, quickly reconstructing the complete memory. This is why, for example, if we smell a rose, we instantly know it's called a rose and we can picture what a rose looks like. With day to day memories, the hippocampus acts like a central router, needing to find where sights, sounds, and tastes are stored, bringing them together for whatever you're trying to remember. But indexing the hippocampus is temporary and fragile. If those hippocampal connections decay or get overwritten by new incoming information, we can no longer connect these pieces of information, even if they're still technically floating around your cortex. So, connections that have been repeatedly replayed through LTP and sleep have grown connections to one another, meaning you no longer need the hippocampus to route the call anymore. Which means that even if the hippocampus is damaged or busy with a new task, this memory remains in the neocortex. So, if our brain makes these permanent connections, why do we forget certain things and remember others? How does the brain choose what it wants to repeat? Well, your brain is bombarded with information, so to prevent your head from exploding, your brain by default is a forgetting machine. It deletes whatever it thinks is useless, but there are three big factors that decide if a memory gets saved or thrown away. First, when something emotional happens, your amygdala dumps stress hormones like adrenaline that act like a neon highlighter that tells the hippocampus, save this immediately, it matters for your survival. So, our brain loves memories that have strong emotions attached to them, which is why we tend to remember the times we've embarrassed ourselves because we felt strong emotions in those moments. Second is novelty. Our brain likes new things. With a routine breakfast that's identical to 500 other breakfasts, there's no unique trigger, so your brain doesn't bother encoding it. But if you happen to try something new that you've never made before, you're much more likely to remember what you ate. And third and last is repetition. Every time you recall a memory or review information, you reactivate that neural circuit. Refiring it tells your brain, hey, we use this path a lot. This leads your brain to insert more AMPA channels, or just make sure that it keeps the existing AMPA channels. This brings us to a phenomenon that you've probably witnessed. Why can older adults describe an event from 50 years ago down to the smell of the room, but struggle to remember what they ate 2 hours ago? Well, neuroscience gives us the answer to this. First, those old memories from youth went through decades of consolidation. They were retold, rethought, and deeply woven into the interconnected networks across the neocortex of our brain. They don't rely on the hippocampus anymore and live permanently in the brain's long-term storage vault. This lack of reliance on the hippocampus is really important because as we age, the hippocampus naturally undergoes mild structural changes and shrinks slightly, making it harder to encode new short-term information into long-term storage. So, likely, only memories that no longer need the hippocampal input will last long into our older years. All that being said, it's still very hard to force our brains to remember things. I'm a student myself, so I know how hard it can be to force our brain to make and strengthen those connections. But I have studied memory extensively as part of my degree. So let me tell you the best possible way to maximize your memory, not only from personal experience, but also from all the best current publications on memory. I'll leave you with 4 tips. These mostly apply to trying to remember things in a school context, but really they can be applied to anything that you want to remember. Number 1 is spaced repetition. Cramming for 5 hours the night before an exam builds weak temporary pathways that fade really fast. Now, those pathways might be there for the morning of the exam, so I'm not saying it won't work. I'm just saying in a week's time, you will not remember anything you crammed. And if you don't care about remembering things after a test, then cramming is honestly fine. But I think it's always important to be knowledgeable, especially if you're using these things for your job later in life. Reviewing material for 20 minutes across 5 separate days forces your hippocampus to repeatedly consolidate this information. So even if you're spending less time studying but spacing it out over a longer period of time, you will likely remember information better. Secondly, you do have to force your brain to work. Sadly. Rereading notes feels easy, but it doesn't trigger LTP very well. Instead, try to close your book and re explain the concept out loud, or test yourself with flashcards. Passively looking at information doesn't force your neurons to communicate, but forcing your brain to retrieve the neural paths makes that path drastically stronger. So, even though rewriting, rereading, or highlighting notes are very popular studying techniques, they're not nearly as helpful for LTP as active recall techniques. Third, we do have to talk about sleep. During REM sleep, your brain relays the day's learning, transferring short term hippocampal memories into long term cortical storage. Sleep is much more important to memory than most people realize. So, even though it's normalized to stay up cramming the night before a test, which I'm absolutely guilty of, sometimes it's better just to go to sleep so that your brain can consolidate everything that you learned that day. Lastly, is exercise. Okay, I know. I'm sure you're bored of hearing that sleep and exercise are necessary, but they really are miracle workers. Cardiovascular exercise increases levels of a protein called BDNF, which actively supports neuroplasticity and promotes the growth of new connections in the hippocampus. This is why there's such a drastic difference in the memories of older folks who exercise versus those who don't. If you speak to an 80-year-old who exercises regularly versus one who doesn't, you will be shocked by the level of difference. It keeps your body healthy and better able to move, yes, but it also keeps your brain working more than people realize. The human brain isn't set in stone. It's a dynamic organ that continuously rewires itself based on what you pay attention to and practice. So, next time you forget where you put your keys or what you had for breakfast, don't beat yourself up about it. Your brain's just being efficient. Thank you so much for watching.